let us switch over to problem number 11. Two identical photocathodes receive light of frequencies f1 and f2. If the velocity of photoelectrons of mass m coming out are respectively v1 and v2, then what is the relation he has asked? The options for this question are given this way. The very first option is v1 square minus v2 square is equal to 2h by m whole multiplied by f1 minus f2. The second option given is v1 plus v2 is equal to 2h by m whole multiplied by f1 minus f2 whole power half. The total value is under root. That is the second option which has been mentioned there. And the third option given is v1 square plus v2 square is equal to 2h by m into f1 plus f2. That is the third option. And fourth option for this problem has been given as v1 v2 is equal to 2h by m whole multiplied by f1 plus f2 whole power half. That is total value is taken under root. These are the four options mentioned there in this problem. Let us now work out and finalize what is the correct option for this particular problem as such. Two identical photocathodes. Identical, the word itself means both the photocathodes have got the same work function. That is the identicality there. Otherwise nothing, not in the same rather shape or size or color like. It is in terms of the work function we people are taking the identicality there. So two identical photocathodes receive light of frequencies f1 and f2. If the velocity of the photoelectrons, right, of mass m coming out are v1 and v2 respectively, that is the concept. So what we can understand is, according to the Einstein's photoelectric equation, we can now write the frequencies are given f1 and f2. Velocities of photoelectrons emitted are given v1 and v2. Let us write two separate equations by taking these pairs of values. So let us write first of all this way. H into f1 is equal to w naught plus half m into v1 square. That is the first equation which I can write. Exactly in the same manner, when the frequency of incident light is f2, then the emitted electron's velocity has been given as v2 there. So let us once again write the same. H times f2 is now going to be w naught plus half m into v2 square. This is our second equation. Only thing you should understand while writing these equations is, since both the photocathodes are identical by nature, one should consider that both of them have got the same work function value. That is the point. Now simple, just take the difference of these two equations please. So what will you get now in this case? Half m into v1 square minus v2 square is equal to h into f1 minus f2. That is actually the concept what I can write. But according to the options given, he is talking about velocities and differences of velocities, sum of velocities like that. He has given four different options. So let us write from this one, v1 square minus v2 square is equal to 2h by m into f1 minus f2. This must be the correct relation between velocities and frequencies what have been given in the problem. So we can write v1 square minus v2 square is equal to 2h by m into f1 minus f2. Look at those options what I have read earlier. The very first option is exactly tallying with the outcome of our calculation here. So the correct answer for this particular problem number 1 is, that is problem number 11 is A. So that is actually the concept what we have to understand. In fact, problem is not something new. Only thing one should identify in this model question is that identical photocathodes, that means they have the same value of work function, nothing else, not the color that is to be considered, not the size that is to be considered, not the shape that is to be considered, excepting the work function, nothing else we need to take in terms of their shape or size or anything like that. That is question number 11 what we have in this order. Look at the next problem, that is problem 12. A photocell is illuminated by a small bright source of light placed 1 meter away. When the same source of light is placed half a meter away, the number of electrons emitted by photocathode would. He gave 4 options once again. The first option says decrease by a factor of 2. Second option, increase by a factor of 2. And third option, again decrease by a factor of 4. And fourth option, increase by a factor of 4. Factor of 4, factor of 2 means so many times like is his idea. And this particular problem has been given in 2005 in AIEEE paper. So one should understand what kind of a model they used to give in the final examinations like. So what is his concept here? Photocell is placed at a distance 1 meter first from the source of light. Now the same photocell is placed from the same source at a distance half a meter from it. So one should understand in this particular case the intensity of light, whatever that is falling on this particular photocell, that is going to obey inverse square law. And we people can certainly understand number of photoelectrons emitted is directly proportional to the intensity of incident radiation. So 2 things you people have to club here. What is the very first one? Look at the thing first. Intensity obeys inverse square law. You all can understand what is this inverse square law. Intensity is inversely proportional to the square of the distance to that source what has been placed there. Intensity of light, whatever is incident on this photocathode or photocell overall I am talking, that now obeys inverse square law. First point. And what else we have to understand here? Number of photoelectrons emitted. Observe this wording. Number of photoelectrons emitted. This is directly proportional to intensity of incident radiation. That is the concept you need to understand. So number of photoelectrons emitted is proportional to intensity, and intensity is obeying inverse square law. Then why can't you directly understand number of photoelectrons which is proportional to intensity, that is inversely proportional to square of the distance of separation between the source and the photocell? So club these 2 straight away. What I can write? N1 by N2 is R2 square by R1 square. What is this R2 now? It's R by 2 whole square. R1, that is R by 2 in the sense what? Half of that original distance I am talking. He gave 1 meter, but okay, this I can take R square. So in other words, you can write this way, 1 by 2 whole square by 1 square. That is what actually has been given. This is as well equivalent to 1 by 4. So what you can write from this one, N2 now becomes 4 times N1. So what is the meaning of this one? Come on, put it in words. When you put it in words, the number of electrons produced or released from the surface of the photocathode now is 4 times the number which was released earlier. That means, can't you understand, it increases by a factor 4 now. So what you can understand here, it is increasing by a factor 4 means correct option over there is now going to be the 4th option. So what we should understand here means 2 different concepts. Intensity that obeys inverse square law, that's one area we have to go for. And second point, number of photoelectrons released from the surface of photocathode is directly proportional to the intensity of incident radiation. In fact, you people might have discussed about laws of photoelectric emission. Number of photoelectrons is proportional to intensity. Energy of emitted photoelectron is directly proportional to the frequency of incident radiation. These two are very important concepts, which of course you might have read them as laws of photoelectric emission. Out of them, the first one I am taking up here to solve this problem. The correct answer for this problem is D. That is the case of problem number 12. Let us check the next number, problem 13, which also has been given earlier in 2006 IEEE paper. The threshold wavelength for a metallic surface corresponds to an energy of 6.2 electron volt and the stopping potential for a radiation incident on this surface is 5 volt. The incident radiation lies in which region? That is the question. Which region means he has given 4 options: X-ray region, and second option is ultraviolet region, UV region, and third option is infrared region, IR region, and of course the fourth option is visible region as such. In fact, we all can understand 4000 to 7500 angstroms when you take the wavelength range, that is visible region of light, which we can see directly by naked eye. 4000 to 7500, that is the range generally what we used to consider. Angstroms I am talking. If you just move towards left, you will be finding ultraviolet region. Right from 100 to 4000 you will be having the wavelength range. Less than 100, generally less than 10 also sometimes we people used to take, that falls in X-ray region. And more than 7500 if you move towards your right in the total spectrum, electromagnetic spectrum I am talking about, that now will be in infrared region. So now you have to decide into which region the incident radiation that falls now. That's the concept. Now look at the values provided to us in the problem. The threshold wavelength for a metallic surface corresponds to an energy of 6.2 electron volt and stopping potential for a radiation incident on this surface is 5 volt. So you can understand straight away H nu, that is now going to be 6.2 electron volt he gave. That is the energy of incident radiation straight away he is talking about. That is threshold wavelength for a metallic surface corresponds to the energy of that. This is H nu naught, which we should consider that one as work function. Observe carefully in this particular case, please. Threshold wavelength for a metallic surface corresponds to an energy of 6.2 electron volt. That means that 6.2 electron volt energy is now corresponding to that energy in which we used to find this threshold value of wavelength. That's nothing other than work function is this much. That is what has been provided in the problem. What else he said? Stopping potential is given 5 volt. You can understand stopping potential. This stopping potential is nothing other than the negative potential at which photoelectric emission stops. It is that reverse potential applied across the photocell at which no photoelectron is going to be emitted from that photocathode. That is the concept. That is given 5 volt means what will be the corresponding energy of this value? It is simply 5 electron volt. All of you know 1 volt, the corresponding energy is 1 electron volt. 2 volts it is 2 electron volt, 5 volt it is 5 electron volts of energy corresponding to this. Now, what is our equation? H nu is equal to H nu naught plus EV naught. This EV naught is nothing other than half mv square. That is the kinetic energy of that emitted photoelectron. In this particular problem, this in terms of stopping potential is given, therefore, I am writing it like EV naught. So, what are the values given here? You see 6.2 plus 5, totally 11.2 electron volt you are getting. That is the total energy of that incident radiation. But what he is asking you is not that. He is not asking you what is the total energy of the incident radiation or something like that. Incident radiation into which region it falls, whether it is X-ray region or ultraviolet or infrared or visible. Out of the 4 you have to pick up one. For that purpose you calculate what is the corresponding wavelength there. Wavelength in shortcut methodology, you all know 12,400 divided by 11.2 electron volt. When I just simplify this one, I get the answer in angstrom units. In fact, all of you know this particular conversion very well. Same thing we people are adopting once again here. If you simplify this value, your answer will be around 1100 you will be getting. How much you will be getting there? Around 1100 angstroms you will be getting here. So, nearly 1100 angstrom units you will be getting. And all of you can understand well, between 4000 angstroms and 7500 angstroms, you will be finding visible region. This is visible region. Greater than 7500 angstroms, that of course comes under infrared region. Less than 4000, that of course till what extent around between 100 and 4000 angstroms, like roughly we can take that angstrom units I am talking. That now will be, right, ultraviolet region, UV region we used to call it. Look at that region over here. It is now to be written this way. It is between 100 angstroms to 4000 angstroms. You will be finding ultraviolet region. Look at this value now. 1100 angstrom units is certainly in this particular region now. So, which region that particular incident ray belongs to? Straight away you can come to that conclusion, it must be ultraviolet region. Must be ultraviolet region means which is the correct option there? It is the second option which has been given to us as ultraviolet region. Therefore, the correct answer for this one is going to be simply B like this. So, this is the methodology what you people have to adopt. In reality, you need not simplify this one till the end, like roughly you can estimate. Only that region we have to say, because all the regions whatever we are talking about between 4,000, 7,500, more than 7,500 up to 10 lakhs, like the different values we used to write, they are all not accurate and exact. They are only the ranges. Therefore, even if it is rough calculation also, you will be finding that this value is going to be well within the ultraviolet region. So, correct answer for this problem 13 is going to be the second option, which of course implies the incident radiation belongs to ultraviolet region. That is the concept. Check the problem number 14 now. This has been given in IIT screening examination paper way back in 2004. One of the wonderful questions based on the graph which has been plotted between photocurrent and anode potential in the case of a photo cell. What is the question? Let me read out. The figure shows the variation of photocurrent with anode potential for a photosensitive surface for 3 different radiations. Let IA, IB and IC be the intensities, and FA, FB and FC be the frequencies for the curves A, B and C respectively. Then he has given 4 options. The very first option is FA is equal to FB. That means frequencies are equal, he is talking about. And IA is not equal to IB. And second option, FA and FC are equal, but IA and IC are also equal. And third option, FA and FB are equal, IA and IC are equal. Fourth option, FB and FC are equal, IB and IC are also equal. Looking to the graph, you have to identify which is the correct option out of the 4 given. Look at now, what is that he has given you? I just mentioned the graph which has been provided to us. He just has taken anode potential on x-axis. This is the anode potential what has been taken. Anode potential, fine. And here this side he has taken photo current, that is photoelectric current he has just taken up. That photo current he just has given here. And he has just drawn 3 different curves over here. One curve he has just given it like this. The second curve has been started from the same point, but it has been culminated at a higher range. And the third curve started from here, but it is joined with this. Look at this graph carefully first, what has been mentioned. And for all the 3 different curves what have been mentioned, he has named them. This is A, this is B, this is C, this is the origin. In fact, when you plot a graph between anode potential and photoelectric current, the potential which you people are getting towards the negative x-axis, that gives you stopping potential. So, you all can understand now, this is the stopping potential for the first curve as well as for the second curve. And this one is the stopping potential for the other curve, that is of 3. So, stopping potential we represent that one with V0. This V0 is of what? This is of A and B. For both the curves the same V0. and this one is of C, that is the third curve is having this as the work function, this one stopping potential. But all of you can understand well in this particular concept. If you take this stopping potential, half mv square is the kinetic energy we know, that now can be written as EV naught, and the same you can even write it as H into F, H nu. So what you people can understand in this particular case is frequency is proportional to this stopping potential. Frequency is proportional to stopping potential. That in the sense what you should understand. Since stopping potential for both the curves is same, what we should write? Frequency of A must be equal to frequency of B. That is one point which you people can certainly understand from the first pair of curves. Now if you look at all the four options, in first option we have FA is equal to FB, and in the third option also we have FA is equal to FB. So out of the two we have to pick up the right one there. Now the question is, for this first curve, this is just the saturation current. For the second curve, this is the saturation current. If I write this intensity as IA and this intensity of SIB, can't you just understand by looking to these two graphs, IB is greater than IA. So the intensity in the second case is more when comparing to the intensity in the first case. So when IB is greater than IA, can't you just write the same equation or same statement that IA is not equal to IB? One is greater than the other one means what? Simply speaking, they are not equal. Not equal in the sense, you see the very first option now. What is the first option given? FA is equal to FB and IA is not equal to IB. That is the concept. So both of course we people have obtained there. So automatically our answer stands as A. So the correct answer for this particular question or the problem here is A now. So their frequencies are going to be equal, but intensities are different. Which one is more? If you just look at, you can identify that the intensity of B is greater than the intensity of A. But one thing you can understand more from this. Since B and C have got the same saturation, you can say intensity of B and intensity of C are equal, but their frequencies are not equal. Therefore, the first option is the best one out of the four what have been given to us. So correct option for this problem 14 is going to be A. One of the wonderful questions I have created here, that is simply by taking a graph plotted between anode potential and the electric current in the form of photoelectric current what is produced there. That is problem number 14. Switch over to the next number now. That is problem 15. Light of wavelength 0.6 micrometer from sodium lamp falls on a photocell and causes the emission of photoelectrons, for which the stopping potential is 0.5 volt. With light of wavelength 0.4 micrometer from a sodium lamp, the stopping potential is 1.5 volt. With this data, the value of H by E is how much? That is a question given. Now he has given you 4 different values. Light of wavelength 0.6 micrometer. So first wavelength of that light whatever is incident on the system of that photocell is 0.6 micrometer. Then what has been given there? Stopping potential is observed to be 0.5 volt. I can write directly V0 is going to be 0.5 volt. Now he is telling us with light of wavelength 0.4 micrometer, the stopping potential has become 1.5 volt. So you can write this way 0.4 micrometer, that is lambda 2. You can write the stopping potential, this time is given 1.5 volt. That is the value given there. Now the question is, with this data, what is the value of h by E? That is the question. H is Planck's constant and E is charge on an electron. So h by E, what is that value? You now can observe the four options given. 4 into 10 power minus 59 volt second. Second option 0.25 into 10 power 15 volt second. And third option 4 into 10 power minus 15 volt second. And fourth option 4 into 10 power minus 18 volt second like. So four different options are provided. Now let us check how to just solve this model. You now can write first of all from the first pair of values given, Hc by 0.6 into 10 power minus 6, that is Hc by lambda is equal to W naught plus EV naught. That of course you can write 0.5 E. And taking the second pair of values, you can write Hc by 0.4 into 10 to the power minus 6 is equal to W naught plus 1.5 E. That is EV naught. That is what actually I have taken up. Now you can take this as first equation and this as the second equation. Now simply take the difference of these two. So what can we write now? 2 minus 1. Then automatically W naught gets cancelled. 1.5 minus 0.5, it becomes 1. 1 into E is E. Is equal to Hc if I take common, right? 1 by 0.4 into 10 power minus 6 minus 1 by 0.6 into 10 power minus 6. Now you can directly understand this one. It is 10 to the power minus 6 if you take it out like Hc by 10 power minus 6 into 0.6 minus 0.4. It's going to be 0.2 in the numerator. This now 0.4 into 0.6, you write it as it is, there is nothing wrong in it. Now you can cut this one twice here. This now becomes 1.2. So what is now left over? You check it. H by E, I just want. H by E. So this becomes 10 power 6 going up. 10 to the power minus 6, it goes to the numerator, right? Into 2 into 0.6, it is 1.2 again. Divided by C, that is 3 into 10 to the power 8. Now you can cut this 1.4 times. So what is now left over? 0.4 into this 6 plus 8, that now is going to be 14. So 10 to the power minus 14. 0.4 into 10 power minus 14, that now can be rewritten as 4 into 10 to the power minus 15 volt second. So look at that option, what has been tallied with this one. So what is the option that is tallying with this calculated value now? It is C, 4 into 10 power minus 15 volt second has been given as the third option. So our correct answer for this particular question is going to be simply C. So this is the methodology what we people just have to adopt for working out this particular model. So one of the good models once again he has given you. In terms of stopping potential, we people have written these equations. So far we have not taken with respect to stopping potentials in writing these equations in the previous problems like. So this is the change what you are observing in this particular model of 15, that is problem number 15 for us. Problem 16 now. An alpha particle accelerated through V volt is fired towards a nucleus, its distance of closest approach is r. You can definitely understand what is the distance of closest approach. In general sense, it is that amount of distance at which that particular particle stops before the nucleus without hitting that one. Because of the repulsion, you will be finding this type of distance, that is distance of closest approach. Now, what is the next point he is mentioning in the problem? If a proton is accelerated through the same potential and fired towards the same nucleus, the distance of closest approach of proton will be how much? You can now understand in this particular case by looking to 4 options. First option is given as r, same as before without any change, that is what it means. Second option is 2r, third option is r by 2, and fourth option is r by 4. Which is the correct option for us? We just have to look into. What is the condition for distance of closest approach? Distance of closest approach you can directly understand this way. Half, that is 1 by 4 pi epsilon naught q into small q by r. What is this value? Try to recollect once again. This is the energy that has been lost by the moving charged particle when it is stopping before hitting the nucleus. In fact, you can all understand here, one is alpha particle and one is nucleus. Nucleus also is a very strong positive core. Alpha particle also is positive by nature. There is no chance for them to collide. We know pretty well the repulsion is so much that it can go to very closer distance and it may stop there. What amount of energy it is losing when it is stopping there? That now can be equated with Q times the V. This is the energy gained by the electron, or gained by the alpha particle, or gained by the charged particle in that particular problem. I am not talking of only one particular particle like. In this case, any charged particle, when it is rather accelerated through a potential difference V, what amount of energy that it is going to gain there in that field, you try to understand first. This is the energy what the charged particle gains when it is accelerated through that potential difference. That energy it is losing just because of the repulsion between the nucleus and that charged particle in this particular case. So, both are supposed to be equal. So, what we can understand, you look at now, Q gets cancelled. What is this capital Q here? It is simply the charge on the nucleus onto which this particular charged particle has been bombarded. So, if you look at Q is definitely constant as far as that nucleus is concerned, and 1 by 4 pi epsilon naught anyhow is a constant, we know. So, Q is constant, we can say, 1 by 4 pi epsilon naught is constant, we can say. Then can't you write that the distance of closest approach is inversely proportional to the potential difference applied? Is it not inversely proportional to the potential with which the particle has been accelerated? So, you people can understand in this case, since V is constant, what can we predict now? R remains the same. There will not be any change in the value of distance of closest approach. Another thing you should understand. Here, if you look at carefully, R is independent of independent of charge on the particle. Charge on the particle. To confuse you people, he is just giving two different particles in the problem. First particle is alpha particle, for which the distance of closest approach is given as r. And second particle is a proton having lesser charge and lesser mass than alpha particle. So for the second particle which has been given as a proton, what will be the corresponding distance of closest approach? That is what he is asking. But if you look at here carefully, r is independent of charge. Independent of charge means what? Whether it is a proton or alpha particle or deuterium ion or tritium ion or any other positively charged ion, you will not find any variation as far as r is concerned, as long as V remains constant. In this problem, he has very clearly mentioned in the problem that if a proton is accelerated through the same potential, so potential through which the alpha particle has been accelerated earlier and potential through which the proton is accelerated now, both the potential values are equal. Therefore, R will not vary. So, R remains the same. Then what will be the correct answer for this particular problem? It is simply A. R is unchanged. That is the concept. So, this is actually the concept you should understand. And what is the principle to calculate the distance of closest approach there? The energy gained when it is accelerated itself is equal to the energy lost when it is being stopped there. So, these two you equate and finalize the value of R, that itself we call it as distance of closest approach in this particular case. So, the correct answer is A, that means R will not be varied, it remains the same for both the particles. Switch over to the next number now, that is 17, which is based on Rutherford's alpha ray scattering experiment. One of the important most concepts before determining what exactly is nucleus, what is the general structure of an atom. In all these concepts, of course, the very first experiment in fact which has given us more information regarding an atom, that was Rutherford's experiment. So, if you look at this problem, in Rutherford's experiment, the number of alpha particles scattered through an angle 60 degrees is 112 per minute. Then the number of alpha particles scattered through an angle of 90 degrees per minute by the same nucleus is how much? Number of alpha particles which have been scattered at an angle 60 degrees is given as 112. At an angle 90 degrees, how much is the number? What is the number there? Options are given this way. First option 28, second option 112, third option 12.5 and fourth option simply 7. Which is the correct option now we have to look into? Probably all of you might be knowing that the number of alpha particles is proportional to z square by sine to the power 4 theta by 2. This is the equation what you people just have to remember, and you might have read this one earlier also. What is what out of it? Let me explain you. Z is going to be the atomic number of that nucleus which of course is scattering these alpha particles. And of course theta here is angle of scattering, and n here gives number of alpha particles which have been scattered at that angle theta, or which have been scattered by the nucleus at that angle theta. So what we can understand, since the same nucleus is taken in both the cases, z square will definitely be a constant, forget that. Now what can we write now? n1 by n2, that now becomes sine to the power 4 theta 1 by 2 by, that is theta 2 by 2 first, sine to the power 4 theta 1 by 2. So simply speaking, you can rewrite the same this way also. N alpha is inversely proportional to sine to the power 4 theta by 2. That is the equation. That only I have taken in the form of a ratio. So what can we write now? N1 is given in the problem as 112 per minute by N2, that is to be calculated. Sine to the power 4 theta by 2, theta 2 by 2, it is now 45 degrees. And the first angle that has been mentioned over here is 60 degrees. Therefore, 60 by 2, it now becomes 30 degrees. So you now can rewrite this one directly as sine 45 1 by root 2, sine 30 1 by 2, whole power 4 you can write. So in other words, you can even rewrite the same 2 by root 2 whole power 4. That in fact 2 goes, this root 2 cancels into root 2 times. So how much it will now be? Simply it becomes 4. So what is the value of N2, the question? N2 now becomes 112 by 4. Exactly you will be getting 28. 28 alpha particles per minute at this angle 90 degrees that nucleus used to scatter them. So what can we write? 28 per minute. The number of alpha particles which have been scattered by the nucleus at that angle, that is 90 degrees, is how much is the question? It is now 28 per minute we have got. See the options. This is exactly the very first option which has been mentioned there. So our answer becomes the very first one, that is 28 per minute. That is the concept. So only thing you should understand is this particular result. In fact, this is the formula which is to be remembered. Number of alpha particles scattered at an angle theta by a nucleus having atomic number Z is directly proportional to Z square by sine to the power 4 theta by 2. That is the equation you people have to remember. So one of the good models, this one is, remember thoroughly for the examination purpose. That is problem number 17. Switch over to problem number 18. This also is based on same concept of alpha ray scattering experiment of Rutherford. 1 million electron volt alpha particle is scattered by 60 degrees by gold foil having atomic number 79. The impact parameter is nearly how much? Impact parameter, that's what we just want. First option is given 2 into 10 power minus 13 meter. Second option is given 10 power minus 13 meter. And third option is given 4 into 10 power minus 13 meter. And fourth option is given 6 into 10 to the power minus 13 meter as such. So here he is asking you to calculate what is impact parameter. So let us first of all write what is the energy given. That of course we used to write it as kinetic energy. That is 1 million electron volt, which can be written 1.6 into 10 power minus 13 joule. You all can understand when electron volt is 1.6 into 10 power minus 19 joule. Million means into 10 power 6. So it automatically becomes 1.6 into 10 power minus 13 joule. And angle of scattering, that theta is given 60 degrees. and atomic number of that foil which is scattering the system over here, that is given as 79. These are the values mentioned in the problem. So if you just look at the next one, what is the question he is asking? What is impact parameter? Impact parameter is 1 by 4 pi epsilon naught ZE square cot theta by 2 by kinetic energy of that particle which has been scattered by it. I once again repeat, impact parameter is 1 by 4 pi epsilon naught 1 by 4 pi epsilon naught ZE square into cot theta by 2 by kinetic energy. Every value out of it we know now. This 1 by 4 pi epsilon naught is 9 into 10 power 9, anyhow we all know that. Z being 79, E square is 1.6 into 10 power minus 19 whole square. Cot theta by 2, that now becomes cot 30 degrees, whole divided by 1.6 into 10 to the power minus 13 joule. All the values are known to you. So you just simplify this. Whichever option that is now tallied out of the 4 options mentioned, that will now be your answer. You will be getting this one nearly 2 into 10 to the power minus 13 meter. The answer is near about 2 into 10 power minus 13 meter, which is the very first option that has been mentioned in the problem. So we can say the correct answer for this one is simply A now. So what is the formula you people should remember for impact parameter? It's 1 by 4 pi epsilon naught ZE square cot theta by 2 divided by the kinetic energy of that particle which is being rather deflected there or which has been scattered by that particular nucleus. So if you look at the correct option for this one is near around 2 into 10 power minus 13 meter. So first option will be the correct option for us. So answer for this problem is A, that is problem number 18. Let us switch over to the problem number 19. In Rutherford alpha ray scattering experiment, the angle of scattering of alpha particles for the impact parameter equal to 0 is how much? In fact, impact parameter will be 0 only when the collision is like head on. So what must be the correct angle for impact parameter to become 0? The angle should be 180. So I repeat once again, for impact parameter to be 0, for impact parameter to be 0, theta must be 180 degrees. That of course is possible when you are finding head-on collision, like when it is just coming straight to the nucleus, that alpha particle, it now just goes back. All of you in fact know in Rutherford's experiment, out of around 10,000 alpha particles what he has sent onto the gold foil, one particular particle, alpha particle, has retraced its path back. So that is what you people just have to understand. That is the condition for impact parameter to become 0 there. That is the case. So what must be the angle there? 180 degrees. That means the correct answer for this one is going to be C as given in the options. So that is question number 19 what we people are having. It's purely a theoretical question. One should imagine and one should understand this particular concept by imagining what is the head-on collision between the nucleus and this particular alpha particle. That is the one what we have to understand. Check the problem number 20 now. From this number onwards, we have picked up few models based on X-rays, Compton shift, Compton effect like, and of course de Broglie's hypothesis as well, dual nature. So the very first number in this order, that is 20th problem. A potential difference of 60 kilovolt is applied across the ends of an X-ray tube. The energy of the most energetic X-ray photon will be how much? You can now understand by looking to the options. First option is given 9.6 into 10 power minus 19 joule. And second option is given 9.6 into 10 power minus 15 joule. And third option 9.6 into 10 power minus 16 joule. And fourth option 9.6 into 10 power minus 17 joule. In X-rays, the production of X-rays and other things when you consider, I remind you, a long chain with different equations. If you can remember all those, that particular chain having relation between different quantities, any problem that comes on X-rays, you can solve that one easily. If you look at this point first, in the case of an X-ray tube, we are going to apply some potential difference across the X-ray tube first. That potential difference generally will be 50 kilovolt, 60 kilovolt, 70 kilovolt like that. 50,000 volt, 60,000 volt, 70,000 volt like that we will be having. When we are just taking up that voltage, then automatically the electron which is released from the cathode, that now will gain so much of kinetic energy due to this external potential difference applied across the X-ray tube. So what we should understand, this EV stands for energy gained by the electron when we apply a potential difference V across the terminals of an X-ray tube. This now will be in the form of half mv square. You can all understand well what kind of energy that can be produced in the case of that electron. With the energy whatever it has gained in that field of potential difference V, that electron now moves faster than before. Electron moving faster than before means certainly its kinetic energy is going to be increased. So the energy gained will be in the form of kinetic energy in the electron. This kinetic energy, suppose the total kinetic energy is converted into an X-ray. That time, what will be the energy of that X-ray produced? It is h nu. The entire kinetic energy, suppose is converted into the form of a photon, which is an X-ray photon there, then half mv square will be h nu. This h nu can even be rewritten as hc by lambda. That even can be rewritten as 12,400 by lambda taken in angstrom units. Then what will be your answer in? That answer will be in electron volt. You also know that point well. If you can remember this chain, let the problem be anything on X-rays. By just equating the corresponding values over there from that chain, you can finalize your answer. Now look at in this problem, which two different equations are to be equated. Look at that problem. A potential difference of 60 kilovolt is applied across the ends of an X-ray tube. Energy of most energetic X-ray When will you find most energetic X-ray here? If the entire kinetic energy gained by the electron is totally converted into an X-ray, then very highly energetic X-ray can be produced. So what is your conclusion here now? Come on, the energy we just want, that energy of X-ray. Energy of X-ray, how much it should be? That now must be EV. Simple. What is this value of E? 1.6 into 10 to the power minus 19 coulomb. And what is this V? 60 kilovolt. That is the applied potential difference across the X-ray tube. So you can write 60,000 directly you can write. Now just cut 1, 2, 3, 4 zeros here, minus 15. So whatever the value you are going to get over here. So it now becomes 9.6 into 10 to the power minus 15, right? What? Joule. So 9.6 into 10 power minus 15 joule if you take here, right? So totally 9.6 into 10 to the power minus 15 joule. If you look at this value, what are the values mentioned you see there? 9.6 into 10 to the power minus 19, first option. 9.6 into 10 power minus 15 joule, the second option. Certainly the answer will now be coincided with the second option. So you can directly understand 60,000 volt is applied across the X-ray tube. Corresponding energy gained by the electron itself is going to be the highest energetical X-ray which is released over there. So directly you can calculate EV and call that itself is the energy of X-ray released. That is the concept. So correct option for this one is going to be B for this problem number 20. Switch over to 21st problem now. That also is on X-rays only. An X-ray tube operates at a potential of 100 kilovolt and 10 milliampere tube current. He has given voltage and he has given the current in the system. But he is giving a wonderful condition here. If only 1% of the electrical power is converted into X-rays. Out of the entire power what actually we are finding, only 1% of the power is producing X-rays. Then how much is not producing? 99% is not producing X-rays. Only 1% is converted into X-rays. 99% is not converted into X-rays means what is happening with that? That energy certainly heats up the target. That is what he is asking you. If only 1% of the electrical power is converted into X-rays, the rate at which the target is heated is how much? So you have been given the options this way: 990 watt, the first option. Second option 99 watt. Third option 100 watt and fourth option 1000 watt. The only thing you should understand here is, first of all, what is electric power? What is electric power in general? Voltage into current. You can definitely understand that one. Voltage is given as 100 kilo, that is 10 cube. Current is given 10 milliampere, so 10 milli, 10 power minus 3. Whatever the value you get, that is in watt. Now you can cut these two. Simply you are getting 1000 watt as the power officially. Fine. But now apply the clause what he is giving, the condition what he is giving. 1% out of this 1000 only is producing X-rays. That means 99% of this power is simply heating up the target. That is very, very clear there in the wording. So, at what rate the target is being heated? That is the question he is asking. So, the target is being heated up by what rate? 99% of 1000. So, 99% why we people are taking up, you can guess now, only 1% is producing X-rays. 99% is now heating up the particular target. Therefore, rate at which the target is heated. The target is heated. That is what he is asking. That's simply 99% of the total power. So, you can just cancel these two zeros to write this one as 990 watt. So, out of 1000 watt of total power, 10 watt only is utilized for the X-rays to be liberated. The remaining simply is being used or utilized to heat up the target what has been taken in that X-ray tube. So, that is what he is asking. So, 990 watt, that is nothing other than the very first option for us of this particular problem. So, 990 watt is the rate at which the target is being heated. That is the concept what we have to understand. So, question is very simple, but that 1%, try to understand that what has been given. 1% is utilized means 99% is not utilized by that system to liberate X-rays. That is the only point you have to understand. Next one is problem number 22. An X-ray tube produces a continuous spectrum of radiation with its shortest wavelength of 45 into 10 power minus 2 angstroms. In fact, one should understand in this case, when you talk about continuous X-ray spectrum, at any voltage across that X-ray tube, that curve starts with a minimum wavelength of X-rays, below which X-rays are not produced at that voltage. We know that itself is called shortest wavelength range. That's what has been given here as 45 into 10 power minus 2 angstrom units. The maximum energy of a photon in the radiation in electron volt is how much? So, what are the values given first of all? Let us check first. It is lambda that is given first. It's a wavelength, that to minimum wavelength he gave. Wavelength when it is minimum, the energy will definitely be maximum. Why? Because when wavelength is minimum, frequency will be maximum. When frequency is maximum, energy automatically will be maximum. That is a point what you have to understand. That is why he is asking you to calculate maximum energy of a photon, not minimum energy. Okay, so that is a point. So, if lambda if you take, it is 45 into 10 power minus 2 angstrom units. 45 into 10 to the power minus 2 angstrom units. This I can rewrite it like this as 45 into 10 power minus 12 meter. Every one of you are familiar with 1 angstrom is 10 power minus 10 meter. That's a conversion factor which all of us we know. And what is his question next? He is asking you to calculate energy. That energy now can be taken as simply hc by lambda. And he has given you the value of h in the problem, the value of c also in the problem. That is one positive point you find in JEE exam. Whatever the constants we require for different problems given in the paper, all those constants he will give you the data. You need not unnecessarily break your head which value to be taken for that constant and other things like. So, if you take h here, that is given 6.62 into 10 to the power minus 34 joule second. in fact that is a standard value, right, into the value of c that is given 3 into 10 to the power 8 meter per second, 3 into 10 power 10 centimeter per second, that is velocity of light, whole divided by this value 45 into 10 power minus 12. But whatever the value you get, that will be in joule. But he is not asking you the answer in joule. He is asking you the answer is to be in electron volt. Therefore, what we should understand? This implies E is equal to 6.62 into 10 to the power minus 34 into 3 into 10 to the power 8 whole divided by 45 into 10 to the power minus 12. Now you divide this one by 1.6 into 10 power minus 19. Whatever the value you get now, that will be in electron volt. But okay, if you think over here, this calculation is looking a little lengthy. However fast you are in calculating things, certainly it takes a little more time. Even few seconds also that count. If you are losing suppose 10-15 seconds in calculating more over here, naturally that may affect the next problem. So, if you want to have the shortcut way, don't work out this way, straight away you take this method. What is that? Energy E is equal to 12,400 by lambda taken in angstrom units directly. What is that lambda given here? 45 into 10 to the power minus 2. Whatever answer you get, that will be in electron volt. Only one step, but anyhow you will be getting a rough value there. And of course, if you look at all the 4 options given, they are not very close to each other. See the very first option, 27,580. And second option they are given is 22,580. And third option he says 17,580. And fourth option is 12,580. The values are not so close. Therefore, estimate like this. Whichever option is nearby your calculated value, come on, adopt that answer. So, which value you are going to get nearly? This value, whether you calculate this way or this way, that energy will be just nearly equal to 27,580. So, what will you get now in this case? This energy E is nearly equal to 27,580 electron volt. So, nearby answer you can pick up. No need for you to waste much of your time in calculating till the last. Directly you can adopt this shortcut method. If you want to go by this, okay, because he has given you the value of H, the value of C and all. But there is no rule, since the answers are not very close. Suppose if he says, for example, first option 27,580, second option 27,579, 78, like that if he gives, then okay, there is no other option, you have to calculate till the end correctly. But now okay, all the 4 options are differently given, there is no rather closeness as far as the numbers are concerned. Therefore, straight away you can adopt the rough method and estimate the correct answer there. This is problem number 22, of which the correct answer is going to be simply the first one, that is A. So, this is also based on the concept of X-rays, what we people have taken up here in this order. Problem number 23 is based on Compton effect. In fact, all of you know very well, when monochromatic X-rays are made to scatter on a carbon block, Compton has observed that the scattered X-rays, few of them are having greater wavelength than that of the wavelength of incident X-rays. This particular observation of Compton has given us a wonderful result. What is that? There is a possibility of transfer of energy from a photon to an electron there. So this is actually what you people have read as far as Compton's effect that is concerned. Now what is the question given here? Let me read out. In Compton scattering, the energy of incident photon is 12.38 electron volt. So you can all understand here, this is energy of incident photon. Incident photon, that of course is nothing other than X-ray there. But okay, incident photon he has given 12.38 electron volt, that has been given there. And what else he is giving? While the energy of scattered photon is 9.4 electron volt. So you can understand energy of scattered photon. This value is now given as around 9.4 electron volt. Now what is the question he can ask? You can directly understand from these two values. What would be the energy of the recoiled electron? Recoiling electron, what is that energy of that recoiling electron he is asking? So look at once again the question I read out. In Compton scattering, the energy of incident photon is 12.38 electron volt, while the energy of the scattered photon is 9.4 electron volt. Then the kinetic energy of the recoiling electron would be nearly how much? First option he gave 2 electron volt, second option he gave 1 electron volt, third option is 4 electron volt, and fourth option is 3 electron volt. So what you should understand here is energy of incident photon. Observe this condition first. That must be equal to energy of scattered photon plus kinetic energy of recoiling electron. That is the concept you need to understand from it. So what is that we want out of this one now? What will now be the kinetic energy of recoiling electron? That is the one which he is asking. Is it not the difference of these two? It's now 12.38 minus 9.4. Had this one be 12.4, I could have got exactly 3. But he is asking you the answer nearly how much? So definitely you can say this one is nearly, right, 3 electron volt. So what is the energy of recoiling electron in this particular case? That is the question he is asking. That's value is nearly 3 electron volt, which of course is the fourth option that has been provided in the problem. So what you should understand in Compton scattering is the energy of incident photon must be the sum of energy of scattered photon and the kinetic energy of that recoiled electron. That is the concept. So if you can understand this, this problem is not a big task. Straight away you can work out the answer there. The correct option is D for this, that is 3 electron volt. Now the problem number 24. This also is based on Compton scattering only. In Compton scattering, X-rays of 1 angstrom are scattered from a carbon block of which the atomic number Z is 6 and a zinc block of which the atomic number Z is 30. at 90 degrees with the incident beam. The ratio of scattered wavelengths is how much? The options are given 1:5 as the first option, 5:1 as the second option, 1:1 the third option, and 1:25 the fourth option. Now one should understand first of all, in Compton scattering, whenever we talk about Compton shift, that of course is delta lambda, which is lambda dash minus lambda h by m naught c into 1 minus cos phi. All of you can understand in this particular case, lambda is the wavelength of incident photon. Lambda dash is the wavelength of the scattered photon. H is Planck's constant, m naught is rest mass of electron, and c is velocity of light. And this phi here, we call it as angle of scattering there. But if you look at this equation carefully, when theta or when phi becomes 90 degrees, that's what has been given in the problem. When phi becomes 90, cos phi becomes 0, that time what happens? Then delta lambda becomes h by m naught c. All of you must have got this idea. When phi, the angle of scattering, is becoming 90 degrees, then whatever is the Compton shift we are finding, that is called as Compton wavelength. So when can we call Compton shift as Compton wavelength? When angle of scattering is becoming 90 degrees, then the so-called delta lambda is, which is equal to h by m naught c, that is now to be called Compton wavelength. Now look at this equation carefully. Here h is constant, m naught the rest mass of an electron, which is 9.11 into 10 power minus 31 kg, that is a constant. See the velocity of light in vacuum, that all of us we know 3 into 10 power 8 meter per second, that also is a constant. So if you look at this, Compton wavelength is going to have a fixed value. What is that value officially? This value is 0.0242 angstrom units. 0.0242 angstrom units, that is a standard value. And if you look at this equation carefully, you can understand one point. What is that? Compton shift is independent of the scatterer. What is the scatterer in the first part? It's a carbon block which is scattering the X-rays. In the second case, zinc block, it is scattering X-rays. So Compton shift is independent of the material of that block which is scattering X-rays there. When it's the case, what we can conclude? Whether it is zinc block or carbon block or some other block, this value is going to be constant for it. So what is the ratio of the wavelengths over here? Then ratio of wavelengths of what? Of scattered X-rays. That's what we are talking of, scattered X-ray, of scattered X-rays will now be how much? 1:1. Whether it is on carbon block or on zinc block or something else hardly matters. It is independent of the nature of the block which is scattering those X-rays. Another you can understand from here itself. Delta lambda is 0.0242 angstroms for carbon block as well as for zinc block. Let the block be anything, it is all immaterial for this. It is independent of the value of Z of that material which is used in the form of a block to scatter these X-rays. So certainly you can understand here, this value is not going to depend on the nature of the material which is used as a scatterer. Therefore, automatically the ratio becomes 1:1, nothing else. So what is the correct option here? It is now the third option which is going to be correct for this problem. So 1:1 is given as C. That is the third option. So that is going to be correct as far as this one is concerned. In fact, you can even remember one more point here. Compton wavelength means a standard value, 0.0242 angstroms. What is going to be maximum Compton shift, they may ask you. When will there be maximum Compton shift? When phi becomes 180 degrees, then Compton shift will be maximum. That will be twice this value. Twice that value means how much it will be? 0.0484 angstroms. That is called maximum Compton shift. Of course, that has not been asked in this problem. Just remember, that's the point. So you can understand here, there will not be any dependency of this wavelength on the material of the scatterer that has been used in Compton effect. That's the point. Problem number 25th number. The wavelength of scattered radiation when it undergoes Compton scattering at an angle 60 degrees by graphite is 2.54 into 10 to the power minus 11 meter. Then the wavelength of incident photon is how much? Wavelength of scattered photon is given and angle of scattering is given, and asking you to calculate what is the wavelength of incident photon in this case. And of course, he has given 4 options. The very first option says 4.2 into 10 power minus 11 meter. And second option is 1.12 into 10 power minus 11 meter. And third option 1.21 into 10 power minus 11 meter. And fourth option 2.42 into 10 power minus 11 meter. Now once again recollect the formula for Compton shift. What are the formula we have written in the previous problem you look at? Right? Compton shift. Compton shift is delta lambda. Lambda dash minus lambda, that is h by m naught c into 1 minus cos phi. I already have explained you earlier. This phi refers to angle of scattering over here. Now of course, given phi is 60 degrees, this implies lambda dash minus lambda now becomes h by m naught c into half. You all can understand this is now 1 by 2. 1 minus 1 by 2 again becomes 1 by 2. That is what I have written here. But you need to remember the value of h by m naught c thoroughly. I have already given you what is that value, h by m naught c, which is called Compton wavelength. It is 0.0242 angstrom units. So you can write this value like this, 0.024. That other 2 you need not write, by 2. So what is this value now? 0.012 angstroms, that is the value. But what did he give? What he has given you, you look at. Wavelength of scattered radiation is given. That means lambda dash is given. He is asking you to calculate what is lambda. So what can we write from this one? Lambda is equal to lambda dash minus 0.012 angstroms. And what is this value of lambda dash mentioned, you see? 2.54 into 10 power minus 11 meter. That's what has been given. That of course you can rewrite like this as lambda dash is equal to 2.54 into 10 power minus 11 can be written as 0.254 into 10 power minus 10. So I write the same thing here, 0.254 angstroms minus 0.012 angstroms. So total, the difference of these two will now be your answer. So what is it you are going to get now? This of course the difference here is 2, here is 4, here is 2, 0.242 angstrom. 0.242 angstrom, that you can write it like this as 2.42 into 10 to the power minus 11 meter. So out of all the 4 options, the 4th option you look at. First option has been given as 4.2 into 10 power minus 11. That's not the correct answer now. 1.12 into 10 power minus 11, the second answer option, that also is not correct. So what is the correct option? 2.42 into 10 power minus 11 meter, which now is going to be the 4th option for us, that is D. So one should understand here H by M naught C value directly you should remember as 0.0242 angstrom units. Remember this value once for all. Otherwise it takes a hell a lot of time for you to calculate that value by writing the values of H, M naught and C there in that equation. So 0.0242 angstroms, straight away you can take it. Accordingly, it becomes now half of that value. Now that you subtract from the value of lambda dash that has been given, then automatically you will be getting the value of wavelength of the incident photon in this particular order. That is question number 25 what we have in this order.